Welcome to section 10.2. In this section we're going to learn about rational exponents, which is actually related to the previous section, which is radicals. And I'm going to show you how they're related first thing. Okay, a rational number, remember, is a fraction. So a rational exponent means that you have a fraction in the exponent like this, 3 to the 1/2, x to the 2/3, -9 to the -1/4. You have a fraction in the exponent. That's a rational exponent. So what does that mean exactly? Well, let's look at this example to figure out what that means. So let's let x equal 3 to the 1/4. Okay, now you're going to wonder why I'm doing this, but it's just to explain what 3 to the 1/4 actually means. I'm going to raise x to the 4th power. If I raise x to the 4th power, that's the same as raising 3 to the 1/4. Also to the 4th power, that's a 1/4 there. Okay, now let's simplify that. 3 to the 1/4 all to the 4th. You would multiply these two exponents by exponent rules. So you would have 3 to the power of 1/4 times 4 is actually 1. In other words, just 3. Okay, so what I just said, let's connect this first piece and this last piece, is that then x to the 4th is equal to 3. Well, if x to the 4th is equal to 3, then that means that x is the same as the 4th root of 3, correct? Because that's what the definition of a 4th root is. Okay, now here we said x is equal to 3 to the 4th. Here we found x is equal to the 4th root of 3. Okay, so what we've shown then is that 3 to the power of 1/4 is the same as the 4th root of 3. Okay, so that is what a rational exponent means. If you have a 1 in the numerator of the rational exponent, such as right here, okay, then the denominator of that rational exponent is the index of the radical. Okay, the denominator of the rational exponent is equal to the index of the radical. All right, so we can work with rational exponents through this understanding of what it in fact means. Okay, let's generalize though so that we're not just looking at a single example. Let's just generalize by saying a to the 1 over n power. So n does have to be a positive integer for this to be true. Okay, if n is a positive whole number integer greater than 1, and if the nth root of a is a real number, that just means that you're not taking, for example, the square root of a negative number or the 4th root of a negative number, so it has to actually exist, then a to the 1 over n is the same as the nth root of a. Okay, make sure that you know that. Alright, so this is something here that you should practice. You really need to pause this video and try to rewrite each of these expressions in radical notation instead of with an exponent on your own, okay, and then check with what I do. So 25 to the 1/2, that denominator right here becomes the index of the radical. Now, normally you don't write the 2 there, okay? That's the square root of 25, which we don't usually write. We usually just write it square root of 25 without the 2. Okay, so that's the equivalent thing in radical notation, and from here you could simplify as well. Okay, x to the 1/5, that's the same as saying the 5th root of x. Alright, -27 times y to the 6th all to the 1/3. Let's rewrite it in radical notation and then use that notation to help us simplify. So first let's rewrite the 1/3 power as a radical. We know that means cubed root of everything inside, which is -27 y to the 6th. Okay, so then we would ask, what is the cubed root of -27? We know that to be -3. And then we have the cubed root of y to the 6th. Now remember, I'm just going to go do some scratch work over here. The nth root of a to the n, if n is even, then that is equal to the absolute value of a, or if n is odd, that equals just a. Now in this case we have a cubed root, okay? So n is odd, so there are no absolute value, it's just a. But what I need to do is rewrite y as something cubed, or the y to the sixth as something cubed. So y to the sixth, if we think of that as y squared all cubed, okay, then we can think of this as the cubed root of y squared cubed. So the cubed root and the cube cancel, and we're just left with y squared. Okay, 27 to the 1/3 means cubed root of 27, which we already know is 3. Negative 25 to the half. Okay, now this is one where order of exponents becomes important. So I'm going to review that. Pause here and review order of operations, I mean. And that's the please excuse my dear Aunt Sally. Okay, this is the order in which you go, and please excuse my dear Aunt Sally is just a memorization tool. But what it really stands for is parentheses, exponents, multiplication and division, and addition and subtraction. Okay, and these are the orders in which you apply them. So first you do things inside of parentheses. Now that part's obvious. Next you apply exponents. Exponents comes before multiplication and division. So this half gets applied to the 25 before we multiply by this -1 out front. Okay, so first we apply the half to the 25 and the negative hangs out front. In other words, what I'm saying is this is not the same as -25 all to the half. Okay, those are two different things. And this up here, if you apply the half to the 25, we would rewrite that as square root of 25. And the negative hangs out front, and so therefore you have -5. Now if the negative had been inside parentheses, this would be not a real number, it's an abbreviation, because there is no square root of a negative number. Okay, again on this one, the exponent gets applied before the multiplication by 7. Notice the 7 is not raised to the power of a fifth. So therefore, the 7 just hangs out front, and we can rewrite x to the 1/5 as the fifth root of x. Okay, so that's some good practice in converting exponents, fractional exponents, into radicals. Now let's look at what happens if the numerator of the rational exponent is not just 1. Notice in all of these, the numerator is always 1 in every single one that we just did. But what if it's a number instead? So say, for example, you have something to, a to the m over n, where m over n could be, m and n could be anything. Okay, since a to the 1 over n is equal to the nth root of a to the m over n, in order to explain what that means, I'm going to first rewrite that as a to the 1 over n all to the power of m. Okay, now I'm unsimplifying as I go from this step to this step, because what I would normally do here is multiply these two exponents, and 1 over n times m is equal to m over n. Alright, now let's rewrite this part inside the parentheses with radicals. A to the 1 over n is equivalent to the nth root of a, and we know that that is all to the power of m. Okay, so another way of saying this is that a to the m over n is equal to, right over here, the nth root of a all to the m. What I'd like to do is write it in a slightly different way, because there's actually two ways you can do this. Instead of splitting it up right here in this order, I could have also written it as a to the m all to the power of 1 over n. So you could also split that fraction up like so. There's no reason it has to be one way or the other, because order of multiplication doesn't matter. X times y is the same as y times x. If we write it this way and then convert the 1 over n to a radical, we end up with the nth root of a to the m, where a to the m is all on the inside of the radical. Okay, so what that tells us is there's actually two ways to express this rational exponent. We can write it like this with the radical, or like this with a radical. So in conclusion, you can say therefore a to the power of m over n is equal to either the nth root of a all to the power of m, or you can write it as the nth root of a to the m. Okay, and if you look at this, basically all it's saying is it doesn't matter whether this m is on the outside of the radical or if it's on the inside of the radical. Okay, because either way you're really just raising something to a power. When you take a radical, you're raising something to a power is what you're really doing. So the order here does not matter. It doesn't matter whether you raise a to the power of m first or last. Okay, so let's work some examples, and we'll use both of these methods here to work these examples, because you'll find that one way is easier without a calculator. In fact, it makes problems so easy often that you don't even need a calculator. Alright, so let's simplify these here. We have 9 to the 3 halves. Now that doesn't really have an intuitive meaning to most of us, because although we know what 9 cubed is, that means 9 times 9 times 9, 9 to the power of 3 halves doesn't really mean much. So it's better to rewrite it as a radical so that we can understand what it actually means. Alright, and there's two ways to rewrite it. One way would be to put the numerator, notice, m is the numerator of that rational exponent, of the rational exponent. One way is to put that numerator inside the radical, the other is to put it outside the radical. So I could write this as either the square root of 9 cubed, or I could write it as the square root of 9 all cubed. That's a 3. Okay, if we do it the first way and we put the cube under the radical, then we must first figure out what is 9 cubed. 9 cubed is 729. I had to do that on my calculator. So then we have the square root of 729, which you would probably need a calculator to figure out. And that happens to be 27. So that method requires a calculator. If we do it this way, and we put the cube on the outside of the radical, then first we take the square root of 9. Well, that's easy. We know that's 3. So then we have 3 cubed, which we can do in our head, is 27. So generally, when actually computing these as numbers, I put the power on the outside of the radical, because that tends to make it more possible to do in my head, though it's good to know that you have an option there. Okay, let me refer to where each of these goes. Remember, the numerator of the fraction in the exponent goes out here or up here. The denominator becomes the index, always becomes the index of the radical. Okay, so this 4 here is going to become the index of the radical. So that means we'll have the 4th root, and actually we still have a negative outside. That is not being raised to the 3/4 power, so negative of the 4th root of 256, and I'm going to write the cube out here. Now you don't really have to write parentheses around that radical, but you can if you want. Okay, so for the 4th root of 256, if you need to use the calculator for that, that is completely fine. The 4th root of 256 is 4, so we have negative 4 cubed, and 4 cubed, let's see, 4 times 4 is 16, 16 times 4 is 64, so we have negative 64. Okay, I definitely would not want to do this the other way and first cube 256, because if you do it in this order, if you do the 4th root of 256 cubed, 256 cubed is, let's see, 167777216. That is quite a large number. And we know we would get 64 there when we took the 4th root, but I wouldn't be surprised if everyone's calculator couldn't even handle that. It's 16 million. Okay. And so try these next few on your own if you haven't already paused the video and tried that. Okay, converting this one into a radical, the 5, the denominator becomes the index. This time the negative is included in the radical because we have this set of parentheses there. So we have the 5th root of negative 32 all squared. 5th root of 32 is 2, and you can take the 5th root of a negative number because 5 is odd, so that would be negative 2 is the 5th root of 32, and then that is squared. Now these parentheses right here are completely essential. You must have these parentheses because we're squaring the whole number negative 2. Okay, so negative 2 squared we know is 4. Alright, we have 1/4 to the power of 3/2. So that would be converting this to a radical. We would have the square root of a 4th, all cubed. Now the square root of a 4th, you might ask what number squared equals a 4th? Well, thinking in terms of fractions, 1 squared is 1 and 2 squared is 4, so that would be a half. And that whole thing is cubed. Cubing a half times a half times a half. The numerators are just going to be 1 because you'll have 1 times 1 times 1 in the numerator, and in the denominator you'll have 2 times 2 times 2, so 8. And then lastly, let's rewrite this expression in radical form. That 7 becomes the index, so that would be the 7th root of 2x plus 1, and that's all squared. And there's nothing you can do to simplify that, it's just that you can rewrite it in radical form. Okay, now you might remember from before, I'm going to make a note off to the side, what a negative exponent means. If you have, say, x to the negative, I'm going to say p for power, that's the same as 1 over x to the positive of p. Okay, so if you have a to the negative m over n, that's the same as 1 over a to the positive m over n. So we're really not doing anything new here. I'm just combining two things now that you have already learned, and that is how to deal with a rational exponent and how to deal with a negative exponent. Okay, so let's rewrite both of these in radical form. Pause this and try it on your own first. Okay, the 3 in the denominator becomes the index, and the 2 will become the power, but before we can do that we really have to handle the negative. Okay, there is an order you have to go in here. You cannot convert this into a radical until you first handle that negative that's in front of the 2/3. So first let's write it with a positive exponent. So to do that we would write it as 1 over 27 to the positive 2/3. Okay, then we can look at this denominator and rewrite it as a radical. So we'd have 1 over the cubed root of 27 all squared. Cubed root of 27 is 3, so 1 over 3 squared, so 1 over 9. That is a simplified form of this number here. Okay, this next one, we have a negative in the exponent and a negative out front. So the negative out front will just hang along. So we'll have the negative of, remember first we have to eliminate the negative in the exponent by putting this in the denominator. So the negative of 256 to the positive 3/4. Okay, then we'll convert that into a radical. So, and I'm going to write the negative up in the numerator just to clean it up a little. So we have negative 1 over the 4th root of 256, all cubed, which 4th root of 256 you might remember from previously is 4. So that's 4 cubed, which is 64. So we get negative 1 over 64. Okay, let's look at exponent rules in general. There's lots of exponent rules here. Okay, if m and n are rational numbers, meaning fractions, a, b, and c are just numbers for which these things exist, basically meaning they're all real numbers. Okay, there's a product rule for exponents, meaning you add the exponents when you have the same base, different exponents. So here we have the same base a and a, different exponents m and n, so you would add those two exponents together to simplify. So you would have a to the m plus n. And let's look at a quick example of that too, one that will make this make a little more sense to you. So I'm going to do an example off to the left here. For example, if you had x squared times x cubed, that means x times x times x times x times x. So you have 5 x's, so that's x to the 5th. Okay, basically if you have the same base and different exponents, you add the 2 plus 3 to get the new exponent. That's what this is saying here. Okay, the power rule for exponents is that if you have a base to a power, and then in parentheses that whole thing is raised to another power, you simplify by multiplying the two powers. So that would become a to the power of m times n. For example, if you have x squared and it's all cubed, that means x squared times x squared times x squared, which is x times x times x times x times x times x. So you'd have 6 x's. How do you get 6? You multiply these two numbers, 2 and 3. And next is the power rule for products and quotients, meaning if two things are being multiplied inside a set of parentheses that is all raised to a power, means you raise both things in the parentheses to that power. So AB all to the power of n is the same as a to the n times b to the n. Or if you have a fraction, same thing. A over c to the power of n is the same as raising the numerator to the power of n and raising the denominator to the power of n. So you would have a to the n over c to the n. Okay, the quotient rule for exponents, this one you should already know, is to subtract. So for example, if you had x, let's do x to the 5th over x squared, that's the same as x times x times x times x times x all over x times x. And you know that 2 of those x's cancel, those 2 cancel and those 2 cancel, which leaves you x cubed. So how do you get it? You subtract. 5 minus 2 is equal to 3. So more generally, a to the m over a to the n is equal to a to the m minus n. Okay, a zero exponent, that one's fun. Anything to the 0 power is defined to equal 1, with one exception, and that is that 0 to the 0 is undefined. You can try it on your calculator and you'll get an error. Okay, a negative exponent, as I showed you previously, that's the same as saying 1 over that to the positive of the exponent. So that would be 1 over a to the positive of n. So these are your exponent rules. You do need to memorize all of these and be capable of using all these. And really, the more that you use them, the better you get with them. There's really not going to be too much to memorize, because hopefully by using them a lot in your homework, you will automatically memorize them without even trying. That's the hope. Alright, so let's use some properties of exponents to simplify these things here. Okay, let's simplify x to the 3rd times x to the 4th. Well, let me scroll back up here. We have same base, 2 different exponents, and they're being multiplied. That looks like this first rule, the product rule for exponents. We have the same base, a and a, different exponents. So how do we combine those? You add the exponents. So that would be x to the power of 1/3 plus 1/4. And this is where you may have to go off to the side with some scratch paper to simplify. What is 1/3 plus 1/4? Let's see, we would need a common denominator. How about 12? 1/3 could be written as 4/12. 1/4 could be written as 3/12. So 4/12 plus 3/12 would equal 7/12. So coming back over here, this is x to the power of 7 over 12. Okay, next example, we have 9 to the 2/5 over 9 to the 12/5. They have the same base and 2 different exponents. So to simplify, we're going to use the quotient rule up here. Same base, right here, different exponents. So we would subtract those two exponents, the exponent in the numerator minus the exponent in the denominator. So this would become 9 to the power of 2/5 minus 12/5. 2/5 minus 12/5 would be negative 10/5. Oops, negative 10/5. And let's keep simplifying. 10 over 5 is the same as 2, so that's 9 to the negative 2 power. Well, we can keep going from there because now we have a negative exponent, which we can rewrite as a positive exponent using this last rule. That's equivalent to 1 over 9 to the positive 2. And 9 squared is 81. So there we have it. Okay, make sure that you're pausing the video and trying all these on your own first, as always. Next we have y to the negative 3/10 times y to the 6/10. We have the same base, y and y, different exponents, and these are being multiplied. Okay, so same base, different exponents being multiplied. That's equivalent to the first rule up here. So we would add the two exponents. So scrolling back down, I would want to add those two exponents. Now this first exponent is negative, but that's okay. You just follow the rules. So negative 3/10 plus 6/10, because I'm adding them together. Let's see, negative 3/10 plus 6/10 is 3/10. And that got rid of the negative exponent right there, so I didn't even ever have to use this bottom rule down here to convert it to a positive exponent because it went away using the first rule. And then there's really nothing else we can do here. We could leave it like this, or we could write it as a radical. You could write it as the 10th root of y cubed. Now either of these is correct. Those are two equivalent answers since it's not specified which form, and it's not obvious which form to get the answer in. Either would do. Okay, on the next one we have a base to a power with parentheses all raised to another power. That looks like this power rule for exponents, a to the m all to the n. In simplifying, we multiply the two exponents. So coming down here, this would give us 11 to the power of, we want to multiply, 2/9 times 3. So that's 11 to the power of, let's see, 2/9 times 3 would be 6/9. And that does reduce. 6/9 is the same as 2/3. Now I can see in my head that this is not going to simplify because the cubed root of 11 is definitely not a rational number. So it would be the cubed root of 11 squared. Either of those forms is correct. And let's look at this last one. This is a bit of a tough one here. We have a negative exponent here, and we have something all being cubed. Actually, we have a product all being cubed. So that numerator, let's look at it first. If we have a product inside a set of parentheses all to a power, means we raise both things inside the set of parentheses all to that power. Therefore, because we have a product right here, 3 times x to the negative 2/3, both the 3 gets cubed and the x to the negative 2/3 also gets cubed. Okay, 3 cubed is 27. And then this, x to the negative 2/3 all cubed. Before we handle that negative exponent, why don't we simplify by multiplying those two exponents using this rule up here, a to the m all to the n, means multiply the exponents. So negative 2/3 times 3. Well, the third and the 3 cancel, so we get x to the negative 2, and that's over x squared. Okay, it's looking quite a bit simpler already. Now we have 27 times these two x's being divided, and we can simplify those because they have the same base and different exponents, and they're being divided. So let's see, same base, different exponents being divided. That's the quotient rule right here. A to the m over a to the n is a to the m minus n. So we do the power in the numerator, minus the power in the denominator. So that would give us 27 times x to the power of negative 2 minus 2. So the power in the numerator is that negative 2. Then minus the 2 in the denominator, which gives us 27 times x to the negative 4. Okay, you could write it like that, or you could write it with a positive exponent, so you could write it as 27 over x to the positive 4. A lot of people will say that negative exponents are not simplified, and maybe they aren't, but they don't exactly bother me that much as long as it really is fully simplified. So I have no problem with negative exponents because sometimes it makes what you're writing much simpler or cleaner to write it out, just to leave the negative exponents there, because you avoid fractions that way. Okay, let's practice using everything we've learned and putting it together with other things that you already have learned. So try these on your own first, of course. So let's multiply this together. X to the 3/4 times x to the 1/4 minus 3. Now you know, if you have something out front of parentheses, you have to distribute it over that plus or minus on the inside of the parentheses. So distributing, we'd have x to the 3/4 times x to the 1/4 minus x to the 3/4 times x cubed. That's just distributing out the x to the 3/4. And now let's simplify. X to the 3/4 times x to the 1/4. Same base, different exponents. So you should add those exponents. 3/4 plus 1/4 is 4/4, which is 1. Minus, okay, same thing here. Same base, different exponents, so we add. We need to figure out what is 3/4 plus 3. That one's a little harder to do. And you don't want to use mixed fractions and just say that's 3 3/4 because that gets really messy and hard to read and difficult to work with. So always go with improper fractions. Okay, that's the same as 3/4 plus, let's see, common denominator. We can write 3 as 12/4. So 3/4 plus 12/4 would be 15/4. So this would be x to the 15/4. And there's really nothing else we can do here except for just not write that power of 1. And we could write this 15/4 as a radical, of course, but that will do right there. And that is a 4. I know it looks kind of like a 9, but it's difficult to write with my pen. Okay, let's do another example. When multiplying two sets of binomials, you should know you have to FOIL. So multiplying your first two together, x to the 4th times x to the 4th. I'm just going to write it like that first. Then the outside terms give us x to the 4th times negative 7. So let's write that as negative 7 x to the 4th. The inside terms give us 1 times x to the 4th. One's easy. And the last two terms give us a minus 7. And from here, let's just clean it up a little. These first two, x to the 4th times x to the 4th, same base, different exponents, so we add 1/4 plus 1/4. Well, we can do that in our heads. 1/4 plus 1/4 is 1/2. Then here we have negative 7x to the 4th plus 1x to the 4th. Now this x to the 4th, you sort of treat it just like it's, well, these are like terms. You treat it just like you would if it was x, and that you have negative 7 of those plus 1 of those, so you add the coefficients. So you would add negative 7 plus 1 to get negative 6 for the coefficient of the new x to the 1/4. And then we have that minus 7 hanging off the end. And you could leave it like that, or you could rewrite it in terms of radicals and write this as the square root of x minus 6 times the 4th root of x minus 7. Okay, factoring. Now this is a slightly challenging thing to do, okay? but you can do it. Factoring, okay. I want to factor out x to the power of negative 1/3 from this expression. Now when you factor, you always factor out the lowest power. So let me bring it in with an example that you already know. Okay, so let's factor just off to the side here. This is just scratch work. If you were to have, say, x to the 5th plus x cubed, and I said factor that, you would hopefully say, okay, I can take 3 x's out of both terms. So you would factor out 3 x's, or x cubed, and you'd be left with x squared plus 1. Now the reason you chose to factor out 3 x's is that because between these two numbers, 5 and 3, 3 is the smaller of those two numbers. And you always basically factor out the smallest exponent. And that rule applies, factoring out the smallest exponent, even if the exponents are negative or fractions or whatever, you just always factor out the smallest exponent, okay? In this case, negative 1/3 is a smaller number than 5/3, than positive 5/3. So that's what you can factor out from both of those terms. Alright, then how do you figure out what you're left with? How did we figure out a 2 goes here? Well, that's because we know that when we re-expand this, x cubed, we say x cubed times what is going to give me x to the 5th. Or you can just subtract and do the 5 minus 3 to get that exponent right there of 2. Oops, that should say 5 minus 3 equals 2. And that's how we knew to put a power of 2 there. Oops, I'm pointing at the wrong things here. 5 minus 3 is equal to 2. There we go. Okay, so let's now, using the same process that you know how to factor, factor out a fractional negative exponent from an expression. So I'm going to start by rewriting the expression. Okay, now let's take out an x to the negative 1/3, and then we'll figure out what we're left with. The first term obviously is going to have a 7 in it. And it'll be 7 times x to some power that goes right there. So let's see if we can figure out what power that is. Again, you could do this method up here and subtract and do that power minus the power that you're factoring out to get the power that goes here. I think that'll be the easiest way. So if we do the original power is negative 1/3. Oh, look at this. Minus the power I'm factoring out minus negative 1/3, this one should be obvious. Negative 1/3 plus 1/3 is 0, right? And that makes sense. It should be a power of 0 there because x to the 0 is 1, and we actually don't need any x's because we factored the whole thing out. We factored out x to the negative 1/3, so we're just left with 7 in that first term. Okay, so that's really just equal to 1, so we really just have a 7 there. Then we have a minus 5 times x to some power. This one we will have to figure out. So let's do the original power, 5/3, minus the power that we factored out, which is negative 1/3. That's 5/3 plus 1/3, which is 6/3, which simplifies to 2. So we should put a 2 for the power there. And I think we should definitely check this one. In fact, if you're factoring out radical exponents, it's always a good idea to check your answer. So let's re-expand this thing out and see if we get the right answer. Okay, expanding the first term is obviously correct. 7 times x to the negative 1/3 is equal to 7 times x to the negative 1/3. Okay, re-expanding the second part, we'll have minus 5 times x to the negative 1/3 times x squared. Okay, simplifying, the first term stays as is. The second term, we have the same base, different exponents, and so we can add those two exponents, negative 1/3 plus 2. Copying. Okay, negative 1/3 plus 2, that's the same. Let's take this up here. as negative a third plus 6/3, which is 5/3. So that will come down here. And that is what we started with originally over here. So it looks like we did factor correctly. I would rewrite this without my scribbles. So let's rewrite this more cleaned up a little. So it's the same as x to the negative a third times 7 minus 5x squared. Okay, now let's practice just simplifying using everything you've learned. Okay, these are all, if you look at these radicals, these are all radicals. So I want to simplify them by using rational exponents. Okay, there are other ways you could simplify, sure, but let's do it by converting all of these radicals to fractional exponents first and then simplifying using those exponent rules instead of using the rules and techniques that we did in the previous section. So this first one, the 10th root of y to the 5th. Okay, if we convert that to a rational exponent, maybe we should write the conversion down here at the bottom. Let's see, the conversion is a to the power of m over n is equal to the nth root of a to the m, or the nth root of a all to the power of m. Okay, so we have something of this middle form here, nth root of a to the m. So that power, the m, the power on the a, becomes the numerator of the fraction, and the index becomes the denominator of the fraction. So this is the same as y to the 5 over 10 power. Okay, and now let's simplify. 5/10 is equivalent to 1/2. Okay, so you could write it like that. That's pretty simple. Or you could reconvert this into a more simple radical, which is just the square root of y. So that was an easy way to simplify using exponents. So let's do another one. The 4th root of 9. That's the same as 9 to the... Now there is no power, so the power is 1. 1 over 4. And there's really nowhere to go with that. The 4th root of 9 is... The square root of 9 is 3, but the 4th root of 9 is not a rational number, so we'll just leave it as that. Okay, next is the 9th root of a to the 6th times n cubed. Okay, so we could rewrite this. Let's see. This one's a little tough because we have two exponents inside of the radical, so that power of m is going to be a little bit hard to extract. So first let's just handle the 9th root, then we'll figure out what the powers are. So one step at a time is what I'm saying. So first let's just write this as a to the 6th times n cubed all to the power of 1/9. Okay, then from here it looks like we could distribute. The 1/9 goes to both things inside because we're multiplying those together on the inside. So that would be a to the 6/9, we use 6 times 1/9, the 6/9, times n to the 3 times a 9th is 3/9. Okay, and then from here we can simplify because both of those fractions reduce. So that's a to the 2/3 times n to the 1/3. And you could write it like that, or you could also, here's another way you could write it. Notice they both have a third in the denominator. So you could write this as a squared times n to the first power all to the power of 1/3. Basically, I'm taking a 1/3 out. That would also be a good answer. These are both definitely both equivalent good answers for this problem that are written with rational exponents. Okay, now let's use rational exponents to rewrite these three expressions here as single radicals. So right as they are, they've all got two radicals, radical and a radical. Let's rewrite them as a single radical. Okay, a lot of this is just practice to help you work with the rules and get them down. Okay, rewriting this as a single radical. Well, the way it's written, we have a square root and a cubed root. Now, square roots and cubed roots cannot just be combined. But if we rewrite them with rational exponents, maybe we can figure out how to combine them. Okay, so I'm going to start by converting each of these to a rational exponent. So the square root of y could be written y to the 1/2. And the cubed root of y could be written y to the 1/3. Okay, now from here I can simplify because we have the same base, different exponents, and we're multiplying. So we would add the exponents. So you would have 1/2 plus 1/3 for the exponent on y. Let's go off into some scratch work over here. 1/2 plus 1/3. We need a common denominator. How about 6? That would give us 3/2 plus 2/6, which is 5/6. So this is equivalent to y to the power of 5/6. Now that we can rewrite as a single radical, which is what the directions say. We could write it as the 6th root of y to the 5th. Okay, which is interesting. Now to get from the original two radicals to a single radical, you did have to actually go through rational exponents and then back to radicals. There's no quick rule that exists for jumping straight from something like that to something like that. No quick way to do it. The only way is to go through rational exponents. Okay, let's practice with this one too. I want to combine the 3rd root of x divided by the 4th root of x into a single radical. Now the 3rd roots and 4th roots don't mix, so let's just first convert them into rational exponents. The 3rd root of x is equivalent to x to the 1/3, and the 4th root of x is equivalent to x to the 1/4. Well, now we can use the subtraction rule because we have x to a power divided by x to a different power. So we would subtract those exponents and we would have 1/3 minus 1/4. Okay, let's figure out what that is. 1/3 minus 1/4. How about a common denominator of 12? So 1/3 is equivalent to 4/12. 1/4 is equivalent to 3/12. 4/12 minus 3/12 is 1/12. So this becomes x to the 1/12. We can rewrite that as a single radical as the 12th root of x. And one last example. Let's multiply the square root of 5 times the cubed root of 2. At first it looks like those cannot mix because one is a square root, one is a cubed root. But if we rewrite them both with rational exponents, we will have 5 to the 1/2, or square root of 5, times 2 to the 1/3. And it doesn't look like those mix because they don't have the same base. So although they're being multiplied, we have two different bases here. Let's rewrite both of these two fractional exponents so that they have the same denominator. Now you might ask why we would want to do that, but you'll see why when we do it, how that helps us to write it as a single radical. So if we write 1/3 and 1/2 with the same denominator, we would need a common denominator of 6. We could rewrite 1/2 as 3/6, and we could rewrite 1/3 as 2/6. Now the reason we would do that is because remember the denominator of the fraction becomes the index of the radical. So those would both be 6th roots. So we could write them as one root by first pulling out a power of 1/6 from both of these, sort of like we did up here. We pulled out a 1/3 from both of those radicals, or from both of those pieces right there. So we could pull out a 1/6 from both of those exponents. So we could write this as 5 cubed times 2 squared, all to the power of 1/6. Right? That's just unsimplifying here, because normally the 1/6 would get multiplied by 5 cubed, and we'd have 5 to the 3/6, and the 1/6 would get multiplied by 2 squared, and we'd have 2 to the 1/3. Okay, now we can simplify the inside of this. Why not? 5 cubed times 2 squared. 5 cubed is 125 times 4. 125 times 4 would be 500. So this is 500 to the power of 1/6, and you can see now that that's a single radical. That's the 6th root of 500. which you might ask, does that simplify? And the way you would tell if it simplifies is to go off to the side and use the division, which we did earlier to simplify radicals. So you would start dividing 500 by small prime numbers. So let's divide 500 by 2 to get 250. We can divide that by 2 to get 125. We can divide that by 5 to get 25. I can divide that by 5 to get 5. And it looks like there's not 6 of any one factor here, so that does not simplify. Okay, so that's it for this section. 10.2, join in next time for 10.3.